So good morning. Thank you for joining us. Joe Foster and I work for Microsemi. We've had a pretty good voyage on security over the years together. I've actually worked with Joe since 2006, I think. Probably the last 2 or 3 years, we've been very focused on bringing security to market for microcontrollers. For Microsemi, that means that in our storage portfolio. So that's kind of why we're talking at this conference about security. So we've got a pretty aggressive agenda. I'm going to try to get through this. This is normally an hour and a half presentation that we're going to get through in 40 minutes or less. But like all good security presentations, I think we're going to provide you with what is the threat model that we're trying to protect against. We'll also spend some time talking about secure boot. It is not the secure boot that is part of UEFI. Secure boot in these cases really refers to making sure that the ASIC can authenticate the firmware that's loaded outside the boundary of the part. So that's how we define secure boot. We'll spend some time talking about attestation, and we'll have a pretty good definition for it in a later slide. But attestation you can think of as, well, I know you booted okay because you didn't stop, but what firmware are you really running? And that's really kind of what attestation is about. We'll also spend some time talking about, at a platform level, how do you establish trust? And there's a lot of proposals in the marketplace that are being kicked around. OCP has an effort, so I'll briefly mention them later. Then we'll talk about secure update, which is basically, hey, I'm going to upgrade the firmware. How do I do it in a way that I know it happened correctly and securely? And then we'll talk about protection through obscurity, which is really about encryption. And then we'll spend some time talking about secure debug. So how this all kind of came about was pretty much globalization. At one point, you built parts in a factory, and you knew the factory, and it was your factory, and you made servers, and you were pretty sure everything that left the manufacturing facility you could count on. If someone messed up, your diagnostics caught it, and if something messed up, you could probably get rid of somebody who did it. In today's world, it's a global supply chain. Parts come from all over the place. Even at Microsemi, while we produce in one foundry, we test in another foundry, and then it goes to a board manufacturer in some other place. And in each one of those, we probably have, 6 things positioned and capable of doing any one of those steps, except for the original silicon that got poured. So it's a long trip. And even at the end of this trip, where it gets boxed up by an OEM, our envisionment is that at any one of these points is a great opportunity to inject new firmware or modify the board in some way that enables a bad guy to move something forward. And there's some really good examples in the marketplace of how this has happened. Major manufacturers have landed servers in locations only to later find out they've been tampered with. And then lastly, in the data center itself, we already have witnessed data center intrusions at a firmware level. There have been situations where virtual machines have been started up for the purposes of simply trying to discover if there's any security holes in the ability to flash firmware, update BIOS, whatever. They have found ways to get in, and you can actually witness someone start up a session for about an hour and then quietly disappear. And it's like, well, why would you provision for an hour? Well, you're provisioning for an hour because you're trying to figure out if you can get in, right? So The question then becomes, how do we prove what it is you're running? So from a threat model, I've kind of mentioned the global supply chain. One thing that's pretty evident now is that I can get anything on the internet I want. So at one point, we developed in ThreatX, and you really couldn't get ThreatX. Well, now you can download ThreatX. We use Green Hill probes. At one time, it was really just between me and my supplier about how to get a Green Hills probe, but now I can buy them on eBay. So I can pretty much instrument at my house all the necessary tools I need to go and perturb firmware that is sitting on a card somewhere. And if I'm a nation state actor, I've got a really good budget, like almost unlimited depending upon what I'm trying to accomplish. So, the other part of that is you think, well, I'll trust the people that work for me. And the real answer is, I'm not really sure I can trust the people that work for me either. If you give them enough money, they'll probably do just about anything. And sometimes they'll even do it in an innocent way. Just insert these 4 lines of code, we'll give you, $4 million, off you go, right? So, and then I'd say from a sophistication standpoint, it's also very clear that these nation-state actors even have production lines where they bring the equipment in, they send it through the process, they box it back up. It looks exactly like it came from the OEM, sealed with the exact right tape. Everything looks perfect. No one would ever know. And again, we already have evidence that those systems actually reached customers and then bad things happened. Or maybe good things, depending upon your point of view. So. One really good example in the news, and we won't spend a lot of time on it, actually happened back in 2015 when it was uncovered. In brief, there were a whole bunch of drive manufacturers whose drive firmware had gotten compromised. At least this is the way I understand the story to read. And someone figured out what their firmware layout was and figured out how to flash firmware. And they actually landed malicious code in the flash on the device itself. And it was almost impossible to get rid of now, because every time the device would boot, the new code would run and be malicious and do things. And things like intercepting the said password. There was an example in this article about how they had intercepted the passwords going to the drive and stored it on flash. And then the bad guy went across our border, and they simply picked up his laptop and were able to decode what was out on the drive. And so there's a lot of examples of this type of thing, but the point of this the point of the article really wasn't about did a drive vendor do something wrong. What it really pointed to was the sophistication of the attack and how they were able to land it on all these different hard drives from different manufacturers. From a customer concern standpoint, we won't spend a lot of time on it, but these are all the things I think that customers worry about. They're worried about gray market products getting into their data center. We've seen this with hard drives and even adapter cards, where you think you're running an official OEM certified device, and you don't really find out about it until something went wrong. And then you call up the OEM and you say, hey, this OEM hard drive X seems to be behaving funny. And you give them the serial number, and they go, oh, that's because it's not really our hard drive. Where'd you get it from? Oh, I got a cheap deal, blah, 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 right? So, but it came in looking just like your product. Anyway, so these are all the things that people worry about. Recovery from exploits. There's actually some good papers out there about how to properly do firmware flashing. We'll cover a little bit of it in this session as well. And then some of my favorites like encryption. So these have been, this is a slightly different customer perspective. I've gotten these requests from either large data center customers or OEMs who are concerned about security. But by example, and we'll actually cover many of these topics, but hardware root of trust for ASICs, continuous firmware monitoring and verification. So the ability to go into your data center and scan all the devices in your system and know the exact version of firmware that it's running, and not only know that it's running, but have proof that it's the right version. Because it's very easy as an attacker to simply say, hey, I'm running this version of firmware, trust me, right? Because you're a firmware stack. You can say anything you want. But we actually have a process via attestation to take measurements of not only the hardware, but take measurements of the firmware that's running. And so through that combination of items, you can actually have, and then sign it with an approved certificate, and then export that content out of that trust zone, and then a trustee can go in and look at that content later. So we'll talk about that a bit as well. So from a market demand perspective, my observation is people are pretty high on this, right? So IBM is continually talking about security in their platforms. Dell EMC has announced, their secure portfolio. I know HP did as well. HPE made a very bold claim. They said they had the most secure servers in the world. Trust us, don't worry. Which I find interesting because you're basically doing the Tony Stark thing. Come and get me, right? If anybody knows the Iron Man movie. From a variety of companies out there that operate large data centers, Cerberus has been announced by Microsoft at Open Compute. There's lots of content around it and security chips. Google and Titan. I think Intel has been moving in that space as well. I think we're moving in many ways from a discussion of the problem set to developments of specifications, even to implementation, right? Because it takes 3 years to get an ASIC out in most cases, from the time you make a decision to the time glass rolls out. And so even at Microsemi, we have been making, good educated guesses about what the market's going to need from a security perspective, and then embodying it in glass, right? And so as you think about it, I think I can safely say we're moving to implementation, right? It's not just a discussion anymore. And if you look at our portfolio, the next generation of products, which I'll have one page on that, shameless plug, you'll see where we're embodying that security in all our parts. And then adjacent to that, we have security parts that we offer separately if you didn't embody the security into your ASIC. So from my perspective, it's about building trust up from the foundry all the way out to the end customer. Because even the user of the content, right, wants to have some assurances that their information is being held securely, that the firmware that's running on that platform is trusted. I personally, when I use my laptop today, really don't believe that I have this trust model very well established. I've got some antivirus software running on there, but God knows what else is really on my laptop. But I shamelessly go through and do all my work on my laptop for banking and all sorts of other things. But when you go to make an offering at a Super 7 or a data center, you really want to have the opportunity to say, hey, I'm from the ground up. And we've even been asked for our RTL inspection on our ASICs. They say, we don't even trust your RTL. We want to see that, right? So they truly have been asking a lot of important questions from an embedded perspective that prior to this was just sort of like, you're protected through obscurity. No one knows how to read RTL. No one can intercept an ASIC foundry. No one's ever done that, right? And it's clear that that's no longer the case. So from a secure boot perspective, what we're really talking about is embedding enough information in the ASIC, okay? And that would be things like public keys, and the code to do the security hashes and decryption. So there's a set of IP blocks and keying material that are embedded in this ASIC that if you believe you got it in there right at the beginning, you can actually begin to validate and improve your circle of trust on the external firmware you load. In our case and many other cases, what we're trying to do is make that first set of code very small, very tight, and very protected, and not modifiable, right? So it's immutable code, and it lives in the ASIC. What happens then is that ASIC, with that code that runs, goes out and reads flash that has a signature adjacent to it, computes the hash of that code, and then compares it to the decrypted version of the signature that was adjacent to the code. And I have a diagram that describes this. And so at each stage of the bootloader, and this is actually like stage 1, actually stage 2. The first thing that ran was in the ASIC. The second thing is it pulls in the first executable that's in flash and runs it. Each stage of that assumes that the prior stage validated it. And so now I can run the next set of code knowing that it's the right code. And I can go validate the next executable that I find in flash. And you slowly build the trust model out for all stages of executables that are found in flash. And so for a storage controller, we have a lot of executables that run. And so each one of those executables gets validated by some prior step. You know,
how much overhead do you have because of that?
How much what?
Overhead. I mean, you're doing this.
So, yeah, let me repeat the question. So if I'm doing all this testing, what's my overhead? Well, from our initial analysis, we believe we are well within PCIe compliance for a device coming up, and we believe we'll meet our own timing requirements that we have from our OEM manufacturers. And today, I think our product launches in something like totally up and running RAID stack, 30 seconds, I believe is our target today from the time power kicks on. That's our measured version. We're available on PCI long before that.
Yes.
I said all the way up to RAID stack running and taking its first I/O. It's 30 seconds.
That's not impacted by security.
That's what I'm getting at. Not impacted by security. We're going to maintain that 30 seconds in the new products. We'll be able to do all these calculations and computations. The main reason we can do it is that within the ASIC, there's a bunch of hardware engines that do hash, do PKA. We do our RSA decrypt with that, and all those sorts of things are all happening in hardware. So we're able to read it. Basically, it takes longer to read it from flash than it does to do the computation, is what it amounts to. I think we had a question on the back.
Yeah, so it's a bit of a tangent, but I noticed you have you've got embedded signing keys in the ASIC. Is that one methodology for, is the same across all the ASICs, or is that unique to Microchip?
As part of POR, we have separate public keys for each of our components. We also have more than one. So we'll have up to 4, and you can revocate the public key if you need to. By that, I need to, I would hope you'd never have to do, because we have the private locked away in our key management system that we use for signing our firmware. And so if you had to revoke a key, it's because we had an escape. And that isn't supposed to happen. Because actually no one sees our private keys, right? They're locked away, they're not visible by anybody, and only the publics are put into the parts, which are fully, I mean, I could hand you the public key and it really wouldn't matter.
Okay, so these are not signing keys, these are signature validation keys. These are the public parts.
These are the public parts of the keys. We put no private information in the ASIC. Pardon?
Oh, you were saying that's private keys.
No. No. In some later work we're doing, these parts may generate their own private keys, right, for individual part identification. But we will not be injecting a private in because, well, neither Joe or I believe you should ever inject keying material. Because what happens is you always end up with a situation where you always have to worry, did someone see it? Did you actually do a unique one? All those kinds of questions come up when you put a software system in place and you're injecting secrets. So we'd actually rather not do that.
Follow-up question there. Do you have any symmetric keys for decryption of any firmware?
So in our product POR, which has not been approved yet, what we would intend to do is be able to store adjacent to the part encrypted firmware. Only that part really needs to know what the key is. And only that part could then generate its own key and store things off chip. We do have capability in the part, in theory, to land other keying material that if we had a request to bring in an encrypted payload from the outside, decrypt it, and store it adjacent, in theory, we could do it. So, and I'll try to repeat the questions next time better. So, all right. So just a little bit about digital signatures. We kind of hinted about it as we went along. In the beginning, you got a developer on the left. He writes a bunch of code. He sends it to our signing service, is what he ends up doing. And in the signing service, it computes a SHA hash of this. And in our case, most products are doing SHA-3, 512. The output of that is, for all practical purposes, encrypted with the private key. And this is what we're calling our signature block. And this information is then stored eventually into flash adjacent to the firmware image that the chip's supposed to be running. Okay? And this private key is stored in a vault. I don't actually, in hindsight, I don't like where that arrow is, but for all extensive purposes, that private key never actually leaves the vault. What actually happens is the information is sent over to the vault and the vault signs it. So I'm actually going to change that. Now, on the flip side, when you do signature validation or verification, the chip actually reads in the firmware again and computes the same SHA hash again. It should match, it's supposed to match. And then it decrypts with the public key the signature that was in flash, and it just does a comparison. It says, well, I decrypted a hash value, I computed a hash value. If they match, I'm happy, and I will now run that code. And we do that at every stage of bootloader. Okay? I don't know why that is up there. Thought I shut everything down. Okay. So, we've kind of been talking about this immutable, mutable trust validation sequence. There are two main types of approaching trust establishment with a secure boot in mind. One of them is I have a system of components where the SoC has no inherent security. And there are now security chips on the market that you can place in between flash and the SoC. And this security chip will hold off the SoC and reset until the security chip has just done what I explained, where you do the signature validation. Now, we could spend a lot of time talking about whether this is secure or not secure. In theory, someone could do a physical attack on this and probably spoof something, right? Or do physical changes to the board. A lot of times in these discussions, we have left physical attack off the table. Because if you have physical access to the card, you could do all sorts of things. In other words, if you could land an IC, you could do an awful lot of things on the board itself. But in any case, some some products do not have inherent security, and so what we've observed is in the market, including Microchip, we've been producing these security chips that are interposer type solutions. But they do exactly the same kinds of things I described, except the security enclave is a separate component. At the same time, which is what I mentioned about all our storage products, we're basically taking that security chip and embedding its intelligence into individual parts. And this is actually a better plan, but that also means you had to have spent some time thinking about it on the front end when you were designing the ASIC. So in our view, you either have embedded security in the part, which we think is inherently more secure, or you can do an interposer solution. And in some cases, you land an interposer solution anyway because you want to use it as a platform of trust. Right? We'll get to that in a minute. So I know the part got booted correctly, and I'm running, but I really have no clue what it is I'm running. Okay? And this is where attestation comes in. So why is that important? Well, perhaps there's a version of firmware with a large security hole in it. Some kind of exploit, a hack, right? And I've decided that I am no longer going to run version 1.1. I'm going to run version 1.2. And you could do a lot of different things to prevent 1.1 from running, but what you really want to do is be able to detect that in the data center everything's running 1.2. So attestation and perhaps maybe the public key got revoked on the hardware, or a security setting that makes the part inherently secure got changed or wasn't enabled in the right way. So attestation can take the measurements of the hardware and the measurements of the firmware and offer up a value to someone who asks for it and say, here's my value. And then you have this other entity, which we'll describe later, which can compare the offered up value to maybe a database of values that it expects to see. And so this other entity can go in and query every device in the system and say, give me your value. There's a lot of discussion about who should give up that value. Like, can you trust running firmware to give up an attestation value? It feels wrong. Who should have nailed that attestation value? And where do you want it stored persistently? Well, you might want it in a write once registry in the part, right? Read it as much as you want, write it once. Who should write it? Maybe something that started running very early in the process versus something running later in the process. Okay? So, and it provides an awful lot of protection. It's just not, like I mentioned, hardware state, software state. And in fact, it may have been perfectly legitimate that you were running version 1.1, but you've just made a corporate decision to run 1.2. Or maybe, depending on what your product is, maybe you have an OEM-specific firmware load that is different from, say, general market firmware load. Okay? And while our part might validate the general market firmware because it had a valid signature and all these other kind of things, maybe the data center really didn't want that in their data center. Attestation would pick up on that. So we kind of touched on it during the last slide. I'll mention it again. And I'm also going to get rid of that. Well, I thought I had actually shut down everything before I started. But so I think earlier I mentioned that the best time to actually grab attestation values is as early in the process as possible, and to land as much of it early in the process as possible. So you want the boot ROM to, that's kind of the PCR values on the right. You would like the boot ROM to land that in registers that are write once at startup. and you would take as many measurements as you could using the bootloader. You would land the hardware state, you would land the firmware verification values, and then you would likely sign it with a private key of the part itself. And this is what I mentioned earlier where I said, hey, it is sort of plan a record that we'd be able to generate on a per part basis a private key, private public key pair actually. So after you take all these measurements, you would likely sign it with your private key. You would also want to incorporate announce. And the reason you'd want to do announce is you want to inject a bit of randomness into the response. And the reason you want to inject sort of randomness into the response to the part is to prevent replay attacks. So if I'm a crafty guy and I've landed ICs on a board, what I might just do is say, well, I saw the attestation value go by yesterday. I'll just replay it back. Okay? And so the announce effectively says, well, even though I saw it last week, it's actually a new value. Okay? And the attester, which sits outside of this system, actually knows that he gave the system announce and knows how to fix the computation for it to come out correctly. Okay? And so then the end state is, well, whoever the attester is has the measurement. It's valid for that particular session, and he can do the comparison and do a thumbs up, thumbs down on what he saw. In addition, there's a lot of discussion today about actually encrypting a lot of this transaction coming out of the part. It might be nice to obscure what's going on between an attester and a specific part. And so there's a lot of discussion in the industry about, well, it's probably not good enough to just sign it. I don't even want them to know what I'm doing, right? And so we're actually talking quite a bit about that. So from a system of trust perspective, we've kind of touched on this a couple of times, but assume this is a server. It doesn't have to be. But today, you got your CPU complex, you've got your BMC. Typically, there's some flash on board. What we've already seen in the industry is I've got some kind of security processor that I actually trust, because I actually don't trust my BMC because it changes a lot. And I actually don't trust the BIOS that's running the CPU much because it too changes a lot. And so what I end up doing is I land this security processor on the platform that is very tight and really only knows how to validate the things that are in SPI flash and then release the other items from reset. So back to that interposer example. I said, well, I'll read it in, I'll validate it, I'll let the BMC come out of reset, I'll let it run. I'll validate BIOS is okay, and I'll let it run. And in some cases, based on one of the specs that got released recently about recovery, you might even have golden images contained within the security chip that bootstraps a system if it detected that there were bad problems going on. And the golden image might only be enough to get the system up and running to flash it again to a good state. Or if you got plenty of room, it might actually restore the entire SPI flash. So this security processor, though, not only does it have that interposer role, but it oftentimes has the role of talking to everything else in the system and validating based on attestation values that everything that's running in the system downstream is also trusted. And this is where I mentioned there's probably this database of content where you have every item listed with every attestation value you expect with the appropriate public key that went with that device so you can decrypt the thing that was sent to you. And so you build up this chain of components, active components, that have security within each of them and report upstream their values, and then the platform knows to trust everything downstream. And we've seen a couple of different things in the marketplace. The most likely thing is you'd shoot one of these active components in the head if you discovered that it wasn't what you thought it was. And then you want a way to recover it, right? So maybe you have an I2C interface to the device, or you have some mechanism to get in and reflash it, or who knows how you did it. But what you really want is the platform root of trust to do the detection and the platform root of trust to do the recovery. So. Boy, this thing is persistent, isn't it? Yeah, I think I am. All right. So I kind of mentioned earlier that what Joe and I would really like to see is verified manufacturing. Okay? And the reason we think this is an important concept is that there's a lot of interesting things that can happen in a foundry. There can be things like floor sweep, where you pick up non-programmed parts and then go give them to somebody to do something nefarious with. Or, gee, a reel of parts just sort of disappear. We don't know what happened to them, right? And then what it turns out is some nefarious person at NSA is building the card, and they just needed some non-secure parts to do it. So our concept is, hey, we should actually certify every chip as it's made and be able to hand over a certificate to someone who asks for it. Okay? And so our view is you will have signed certificates from an authority that when you hand over that part-specific certificate, I can actually prove to you I made it and prove the authenticity of the part. Right? Now, there's a few holes that can occur in that you could end up maybe cloning something. That is a possibility, even in this type of scenario. If you were clever enough, you could clone. But in like a large data center, what would end up happening, right, is you'd go, that's weird. I got two parts with the same certificate. That's really not supposed to happen. And so they would end up pulling the parts, right? So we believe there's quite a bit of detection that might go on, but we believe we can cleanly generate certificates on a part-specific basis based on a secret that is generated out of the chip. And all this is self-contained in the part. Because we believe that the best way to do this is through self-generation versus injection. Injection leads to error, injection leads to interception, injection leads to all sorts of badness. So we believe we'd like to generate it within the part, and then we will sign the public certificate and store the signature back with the part. Okay? So that's kind of what this all adds up to. One comment down at the bottom is, well, two things. One, you could actually re-sign this part. So if you're a company that wants to sign their own parts, that part as it's brought in, you could do what is called a transfer of ownership. And you can say, hey, well, when the part comes in, I will sign it again, and I will store that in the part itself. We would provide utilities to do it. And then you could actually transition ownership from a Microsemi device to a, XYZ company device with their own certificates. And the nice thing about that is, back to our detection problem, if you went out and looked and found that something was running in your data center that you didn't sign, you just go pull it, right? Because your assumption is your signing services are secure. When you bring the parts in, you reprogram them, and then you deploy them. And anything after that happens, you should be able to detect, okay? And then lastly, it is possible because in a lot of these parts, there's actually room to inject additional public key material. So let's say that you're a company and you don't really want to run on Microsemi infrastructure, okay, or any company infrastructure. You don't want our signing services in the middle. So what you ask of us is you say, well, I want my part customized. I'm actually going to stand up my own signing services in my own firmware infrastructure, and I'll compile your code and I'll sign it, and I want my public keys there instead of yours. And so in a lot of our parts, we're making provisions to allow you to inject your own public keying material so that you could stand up a lot of infrastructure. Although our belief is that we very few customers that actually do that, because it's pretty painful. Just managing sources and building code and making sure it worked right and all those sorts of things becomes somewhat intractable.
So in this case, you need access to that code to know what to inject, or is there a place that you always standard place you inject it in the flash code?
So okay, so let me see if I'll restate your question. How did I get the keying material into the part? I think is what you're asking. So within the ASIC itself, there's a non-programmed region of one-time programmable memory. And what we would end up doing is giving that customer a utility that would enable them to put the part in a mode that you can program those values. The second way to do it is that we would actually get the values, because it's public keying material and it doesn't matter who really knows it, we might actually end up injecting it in Foundry. Probably on the tester or subcon. It wouldn't actually go all the way back to where we poured glass. So you could customize the parts on the way out of our factories to put those public keys in place. We might hand you a utility that is secure for landing those public keys within the fuse block. And I think we're doing okay. So from a secure firmware update perspective, there's a fairly well-known spec that got released back in May. I believe it's SP 800-193, but I think that's the one. Sometimes I get them confused. But it's a really good document that describes the right way, I wouldn't say the right way, a good way to do firmware management on a chip. And so this is one of the flows that we kind of pulled out from that specification doc. There's actually some other content that goes with this, like rollback protection, but this is a very simplified one. So on the left, I got running firmware, and I decided to flash the part. And you actually decompress this thing into a non-persistent area, so that if you reboot it again, you wouldn't find the image. It'd be gone. Because a lot of people are worried about malicious code living in flash that never disappeared. It was just deemed invalid. We would run the tests with running firmware that is trusted. And if it's valid, we would actually move it to a persistent area. Now, moving it could be, I flip a bit and identify that area as valid. Moving it could be that I had stored it somewhere else and now I'm actually going to move it to flash. And once I've moved it into a more persistent area, I now end up doing the full secure boot process. So I have to do a reset on the part. And I will actually come up and check everything again. Even though my running firmware said it was okay, if for some reason someone perturbed the running firmware and it looked okay, and it let something through, sending it through the secure boot process again would revalidate the firmware image and prevent that from happening. So I successfully boot. I think life is great, and I'll now move that image back over to my backup copy that sits in flash also, because part of the 193 spec is I need to check it and verify it. I need a place to put it, and I need a place to recover from if things didn't go well. So I actually don't make this copy from firmware area 1 to 2 until after the decision has been made that this thing booted correctly. So after that's been programmed correctly, based on what we knew about the firmware area 1, we then ask the question, did someone revoke a public key? And the reason you do it at this point is that if I did it earlier and I revoked a key, I might not ever boot the device again. Okay, so I got to know that I'm running on the right public key when I do the startup. So I don't ask this question until much later. Now, keep in mind, this should always be no. You should never revoke a public key. right? There may be a few cases where you did, like maybe I changed ownership of a part. That would be an opportunity to blow a key. But in general, that should never happen, okay? And then now you're running redundant firmware again. I just wanted to see. We're going to run out of time. All right, 2 seconds on cryptographic obscurity. I think I mentioned that if you generated if you could put secrets inside the part at foundry time or self-generate them, which is my preference, one of the things you could self-generate out of it is a unique ASIC-specific encryption key. And you could use that unique ASIC encryption key to encrypt all the things on the right, all the data flows. So you can encrypt flash, CPROM where you do settings, and even DRAM potentially, all based on a key that's embedded in the part that the part self-generated. And that's kind of what cryptographic obscurity is about. Secure debug mode. Everybody needs to debug a part at some point or another. And the problem with the debug mode in general is that it's an open door. You get in, you can almost do practically anything to the part, look at anything you want. And so the concept is, in general, you close these down. You don't ever let a JTAG be used, a UART be used. You close them all off because they're just open doors. And so in secure debug mode, you collect enough information from the part to go make a special firmware build that only the part will allow to run. And when you run that debug code that only that specific part will allow you to run, it'll then open up the part in ways that most people wouldn't want. So this is really handy in development. We at Microsemi would end up opening all our parts in debug mode and all our images would be debug. But the neat thing about it is my machine will not run Joe's code. My machine will only run the code that I sign with my private build environment. If I go out to a customer, same thing. I got a machine that's got a problem. I can open up the ports and I can look at it, but that opening only works on that one machine. It won't work on all the others. Real quick, and then I'll be done. There's a number of security projects in the marketplace. This is not an exhaustive list. The Open Compute Security Project, I would invite anybody who's interested in security and helping design security for platforms, get involved. The list today is pretty long. We're currently working on like secure boot and attestation. There's the Intel spec that's been released in draft. I just discovered it was .71 yesterday, released in September. It's got some very good information about how they think securing a platform should be done. The 193 spec is really about firmware management, and grooming, and health, but that's been released. And then, of course, I mentioned Cerberus. And then lastly, part of the reason I haven't actually been at the conference all week is I've been doing this DMTF PMCI security task force on security. So we actually hope to provide some information, more information than just we're working on it soon. Right now we can just say there's a security task force. If you're interested, come join the task force. You can learn all about it. So there you go. And then lastly, shameless plug, we make a lot of products. The ones on the left have embedded security. Everything from storage controllers to PCI switches to UVM controllers, they all have embedded security within them. And then we also sell a bunch of security devices on the right. This is not an exhaustive list of all the security devices we sell. This was just an example set. So. All right, I think I made it. Any additional questions? All right, if you want to talk later, we can. I'll be around for a bit. Thank you.